Hi, so in this video, I want to clarify to make sure that we understand thoroughly the angle theta in this equation, okay? So what is theta? Theta is the angle that is made between on the point at the slit with the point P of inches on the string. So how can we define this theta? This is the angle theta, okay? So it's just like from the slit center S2 and then to the point of inches, we draw a connecting line between these 2 points, okay? And then there's another line that we draw from, let me change the color, from the slit center to the string, okay, and perpendicular to the string. So then this line will demonstrate the distance between the slit to the string. Let's say this is point O. Then you can see that the angle PS2O, this angle here, will be the angle theta, okay? And then again, what is D here? D is the width of the slit, and the slit here is a very narrow one, so D is just like in the millimeter scale. And the distance between the S2 to O will be in the meter scale, okay? So, as we have mentioned earlier, to study the diffraction pattern, we will divide all the points within the slit into pairs, and then each pair will be distant away from each other by half of the slit, okay? So then, you can see that from S2 to the P point of interest, the path for the wave travel will be S2 P, right? Then the distance from S1 to P, also another path that wave travel, it is much. So if we want to study the path difference between these two, I will try to align the S2P onto S1P and just like borrow this point S2 prime here, then we can see that the path difference now becomes S1, S2 prime, right? That will be the path difference. Okay. Now we can see that this triangle here, S2P, S2 prime, will be a isosceles triangle, right? Because it have these side, these two sides equal to each other, right? Okay, that's why you can also have these two angles also equal to each other as well, okay? And the important thing to note for this one is that point P is very far away from the S2 and S1, which means that this angle, is very small. It's a very small angle that it can reach to like a zero value. And that's why you will have these two angles can approximately equals to 90 degrees. Okay, because we know that the angle in a triangle should, when you sum all of them, it should be almost 100. It should be equals to 180 degrees, right? So if this one is very small, then the rest should add up to like 180 degrees. And if you divide it by 2, then it should be approximately 90 degrees. That's why you can see that for now, this red angle here, the S that is the theta angle, right? This is the theta angle that is created between S2P and S2O. And then you can see now S2P almost, we can see that it perpendicular to S2 prime here, right? Because we said that this angle almost 90, okay? Then we also have S2O almost perpendicular is perpendicular to S2, S1. So in math, you should know that an angle between two pairs of sides will equal to each other if the two pairs of sides perpendicular to each other. That's why you can see that the theta angle here will be equals to this angle here. The angle made between the S2 prime, S, and then S2 and then S1. Okay, that's angle. So then you can have this angle also equals to theta. And that's why we can find S1, S2, 1, because now this triangle S2, S2 prime, S1 is a right triangle. Okay, it's a right triangle. A right triangle. Then we got this one will equal to the hypotenuse S1, S2 times with the side of that angle, which also equals to the theta angle. And that's why you got the path difference. The path difference equals to half of the slit times with side of theta. So when you got the point P is a dark fringe at that position, then the path difference will equals to an integer of half of the wavelength. And that's why in the end we got these equations, like in the previous video, right? Here, I just want to emphasize again, how can we got that theta angle equals to the angle here, you know? And this is like for case of the pair we consider is the S1 and S2. S1 is at the edge of the slit and S2 is at the center of the slit. As we have mentioned earlier, we will consider all the sources between the slit into pairs, which always like further away for like half of the width of the slit, right? So let's say you have another pairs like S3 and S4, this one. And you can see that the distance between them also half of the slit as well. It's just like the same distance between S1 and S2, okay? Then now again, you also have a wave travel from S4 to P. And then you also have another wave travel from S3 to P as well. And again, we also need to find the difference, okay? The path difference between S4P, S4P, let me change the pen, okay? S4P and S3P, right? The path difference. In this diagram, we have S3 is like longer than S4 a little bit. And then just again, we also need to have this point as a S3 prime, you know? And also again, this angle approximate to be 90 degrees as well. And that's why you also get the same angle here equals to this angle here. And you can see that this angle here can be approximate to be theta as well. Okay, so that's why in the end, we also have this one like half of this width times with sine theta. Oops, my bad. Also equals to the integer of half of the wavelength. And that's why when you divide all the second sources between the slit into pairs, and each of them just like away from each other, half of the slit, you always got the same expression. And that's the thing that I want to highlight in this video. Just want to clarify again that we assume that we approximate on the angle between on the point here in the slit here, you know, that will make a angle theta with that P point of interest. Okay, so that's why we have an assumption that S2P, S1P, S3P, S4P, or like all the secondary sources between the edges of the slit in the slit, which is like nearly parallel to each other. That's why it will be the same angle theta. Okay, that's the thing that I want to highlight for diffraction pattern. Okay, please let me know if you have any question. Thank you.